Okay, so for what we have in this particular part, we'll be looking at inverses and squares of matrices, and then we'll be looking at solving for a 3-equation system by using an inverse matrix. Okay, but first things first. Okay, so we have with inverses and squares of matrices. Okay, we have for these two problems, it says to determine the inverse of matrix A and the square of matrix A, as well as the square of the inverse of A. And with the first matrix, okay, we have a 2 by 2, whereupon we have 2 and negative 7, as well as 6 and negative 1. And looking at what we have first of all, okay, so we have A times the identity is equal to the identity times the inverse of A. And so looking at what we have in the setup, so you have A with 2, negative 7, 6, negative 1, and alongside what we have with the 2 by 2 arrangement, we have again the 2 by 2 identity, whereupon we have 1, 0, 0, and 1. And looking at what we have taking the transformation going from 2 in the upper left hand section to 1, if I take half of the first row, so I'm going to have 1, negative 7 halves, 1 half, and 0. Okay, so we have, again, the first column, I want for there to be a 1 and 0. So changing the 6 to a 0, I'll be looking at now, taking from the second row, what will be 6 times the top row elements. And for what we have in correspondence, okay, so we have 0, 20, negative 3, and 1. Okay, so for the first column, I have 1, 0, and the next column, I want to have 0 and 1. And I can change this 20 into 1 by taking 1/20th of the newly formed second row. So for what we have in the follow through, okay, so 0, 20, negative 3, 1 will be transformed to 0, 1, negative 3/20ths, and 1/20th. And we have, again, so I got 1 and 0 for the first column. And for the second column, I want to change the negative 7 halves to 0. And doing so, and preserving the 1 at the bottom of the second column, I can just take the first row and add to it 7 halves of the second row elements. And so we have here, okay, so we got, for the first row, we have 1, 0, negative 1/40th, and 7/40ths. And again, we have the bottom row, we have 0, 1, negative 3/20ths, and 1/20th. And if you notice, for the left half of this 2 by 4 arrangement, you have the identity matrix. And for what I have in the right half, this is going to be the inverse of A. So again, we have the top row with negative 1/40th, 7/40ths, and the bottom row we have negative 3/20ths and 1/20th. Okay, now we have for the next portion, so we're looking at the square of matrix A. And again, so we have A times itself, so we have a couple of identical 2 by 2 matrices. And again, if I take A and multiply by its first column, okay, so again, you have in the arrangement, you have 2 times 2, 6, and then you have plus 6 times negative 7, negative 1, so we have negative 38 and 6. And then taking A times its second column elements, and just with the properties again, so we have from the first element in what we have with negative 7, negative 1, so I have negative 7 over 2, 6, and then I have plus or minus 1 over negative 7, negative 1, and we have negative 7, negative 41, and clustering together these 2 by 1 matrices and making into the 2 by 2 matrix product. So we have for A squared, we have for the top row, this will be negative 38, negative 7. Bottom row, we have 6 and negative 41. Now, for the square of the inverse of A, I can do this through either of two approaches. And for the square of the inverse of A, so I have like, again, A to the negative 2. And so this will be the square of A to the negative 1, or the square of the inverse of A. And again, we just arrived at the inverse of A with these 4 fractions. And just taking this, so the square will be that inverse times itself. And going through the arrangements, again, so you have the matrix inverse, okay, times the first column, in that arrangement. And then we have the inverse matrix times, okay, the 2 by 1 matrix formed by the inverse matrix's second column. Okay, and so we have for the first arrangement, okay, so we come out to negative 41 over 1600 at the top. At the bottom we have negative 3 over 800, and we have with, again, the second part, okay, have 7 over 40 times the first column, and then we have plus 1/20th times the second column. And for that combination, I have 7 over 1600, and I have negative 19 over 1800. And so combining these 2 by 1 matrices as a 2 by 2 matrix, so I have the result where we have the square of the inverse of A comes out to negative 41 over 1600 and 7 over 1600 in the top row. And the bottom row we have consisting of negative 3 over 800 and negative 19 over 800 on the bottom. And again, just another way that you could go about this is that the square of the inverse could also be regarded as the inverse of the square of A. And again, from earlier, we had that A squared consists of negative 38, negative 7 in the top row, 6 and negative 41 on the bottom row. And we have with this approach, again, so you have A to the negative 2, okay, we can say from our relation, okay, utilizing the square of A, again, we have with A extended to A squared and the inverse of A extended to A to the negative 2, we can say that A squared I is equal to I times A to the negative 2. And so we have with the 2 by 4 matrix, okay, so you have the square of A alongside the identity. And again, making the negative 38 into a 1, I take negative 1/38 of the first row. I have these elements, and the 6 on the bottom of the first column I can make into a 0 if I take the bottom row and deduct 6 times the elements of the row above. Okay, and so we have in this configuring, we have 0, negative 800 over 19, 3 over 19, and 1. And now I want alongside 1, 0, I want 0, 1. And I can change the negative fraction minus 800 over 19 into 1 by taking the reciprocal and multiplying. So I have negative 19 over 800 times the second row. So now I have 0, 1, and then 3/19, and 1 will be changed over to negative 3 over 800 and negative 19 over 800. And finally, for changing 7/38 to 0, I can take the top row and deduct 7/38 of the bottom row elements. So I have, in the result, I have the top row with 1, 0, negative 41 1600ths, and 7 1600ths. And for what I have on the right, again, it's going to be A to the negative 2. And if you notice, in comparison, we're going to have the exact same 4 elements. All right. Now, for what we have in the case of the second matrix, which we have with a 3 by 3, if I'm looking for the inverse, so A, we have 1, negative 1, 2, 5, 4, 2, 1, negative 3, negative 4. And if I use the property that AI is equal to I times the inverse of A, I can just set what I have here up as a 3 by 6 matrix, have A alongside the identity, and converting the first column to 1, 0, 0. So this will involve taking the second row and deducting 5 times the first row, as well as taking the last row and deducting the elements from the top row. So I have these rows involved. So I got 1, 0, 0, and next column I want 0, 1, 0. And the 9 I can convert to 1 upon taking 1/9 of the second row. So I have 0, 1, negative 8/9, negative 5/9, 1/9, and 0. Okay, so I have 1, 0, 0, and I want to convert the negative 1 and the negative 2 in the second column to zeros. So we can do this by taking R of 1, adding R of 2 to it, and simultaneously adding twice the second row elements to the bottom row. Okay, and so with this configuring, okay, so I got the second column at 0, 1, 0, and I have these columns to be formed alongside 1 0 0 and 0 1 0. Now I want the third column to be 0 0 1 in order to get to the reduced row echelon form. So the negative 79ths I can convert to 1 upon multiplying the third row by negative 9 over 70. In other words, multiplying by the reciprocal. So here I'm going to have 0 0 1, 19 over 70, negative 1 over 35, and negative 9 over 70. And converting the 10 ninths and the negative 8 ninths to 0. Okay, so I'm going to have with the operations, I'm going to take the top row and deduct 10 ninths of the third row, and to go from negative 8 ninths to 0. I can take the second row and add 8 ninths of the third row elements, and doing so I have the third column consisting of 0 0 1, and we have the 3 by 3 arrangement to the right. Okay, we're going to have the inverse of matrix A with 1/7 throughout in the top row. Middle row we have negative 11 35ths, 3 35ths, and negative 4 35ths. And the bottom row we have 19 over 70, negative 1 35th, and minus 9 over 70. All right, now looking at the square of matrix A, so I'm looking at matrix A times itself. And so for what we will have here, just itemizing again the first column, second column, and third column. And so we have with 1 5 1, so you have 1 over the first column, 5 over the second column, 1 over the last column. And so I'm going to have the formation of the first column elements in the product with negative 2, 27, negative 18. And then we have with A times, okay, the second column arrangement forming its individual 3 by 1 matrix. Okay, so we have negative 1 over 1 5 1, then we have 4 over negative 1 4 negative 3, and then I have 3 over 2 2 4, and we have negative 11 5 and negative 1 in the product. And then for the last column elements in the product, so I'm looking at A, and I have times 2 2 negative 4, okay, from the last column in A's duplicate, and just going through the arrangements, you have like your XO1, XO2, XO3, and then you have your AO1, AO2, AO3 arrangement. So you got 2 over the first column, plus 2 over the second column, minus 4 over the last column. And we have, in the result, we have negative 8, 10, and 12. And clustering together the 3 by 1 matrices and putting together as a 3 by 3 matrix, it turns out that the square of A is going to come out to negative 2, negative 11, negative 8 at the top. In the middle, 27, 5, and 10. And finally, we have the last row consisting of negative 18, negative 1, and 12. And for what we have in looking at the square of the inverse of A, and again, we have A to the negative 2 can be regarded as the square of the inverse. And again, we had the inverse with these small fractions. And there was a lot of work involved in this. And so for the inverse times itself, again, you're looking at the inverse matrix, and then you have itemizing the first row, middle row, last row, and then just taking the top number like representing x of 1, and then you had the middle from the 3 by 1 as x of 2, last as x of 3, as we work with these itemized 3 by 1 matrices. So you have, like in the first case, you have 1/7 over the first column, minus 11 35ths over the second column, and then 19 over 70 with the last column. And you have combining, we have these small fractions with 1/70th, negative 18 over 175, and 9 over 700. And then kind of like going with the matrix times the second column. Again, so we have in the arrangement, okay, so just repeating the process, it got 1/7 over the first column. Now we had the middle row term at 3 35ths and distributing over the second column of A. And then finally we have the bottom row at element at negative 1/35th and distributing over the last column of the inverse of A. Okay, and then just looking at combining, so I have 1/35th, negative 670, 1/75th, and then we have with the last product. Okay, so combining the bottom row elements with the coefficients alongside and putting together, I have 1/25th. And then we have with the last column and then multiplying everything out. Again, with 1/7 over 1/7, negative 11/35 in 1970, minus 4/35 over the second column elements. And then we have minus 9 over 70 times the last column elements, and just multiplying what we have with the corresponding parts and putting together. And we had the last column to consist of negative 1/70th, negative 1/25th, and 41 over 700. And for the square of the inverse of A, we're going to have consolidating these 3x1 matrix elements and forming a 3x3 matrix in the result. So you have the top row with 1 over 70, 1 over 35, and negative 1 over 70. The middle row we have at negative 18 over 175, negative 6 over 175, and negative 1/25th. And we have with the last row, we have not negative, but positive 9 over 700, 1/25th, and 41 over 700. And again, if I were to take the approach where I have a to the negative 2 is equal to the inverse of the square of a, I can just say that, just in short, a squared times I. Again, a squared, again, we had arrived at negative 2, negative 11, negative 8 in the top row, 27, 5, and 10 in the middle row, negative 18, negative 1, and 12 in the bottom row. And again, I had the identity matrix alongside it. And again, if I were to perform the row operations, again, I will have the identity matrix on the left and the elements to the right. I come back to the square of the inverse of A. So I have these same values throughout. All right. And now for a system of equations, okay, so if I'm looking at a system that consists of solving for x, y, and z, whereupon x minus y plus 2z is equal to 10, 5x plus 4y plus 2z is equal to 29, and x minus 3y minus 4z is equal to negative 32. So in the setup we have here, so we have A times the solution matrix X is equal to B. And looking at the solution matrix, if I were to isolate upon having arrived at the inverse of A, I'll have the X is equal to the inverse of A times B. But first things first, A, again, we have the coefficient matrix with 1, negative 1, and 2, followed by 5, 4, and 2, and then we have 1, negative 3, and negative 4. And for the solution matrix X, you have a 3x1 arrangement where we have X, Y, and Z. And again, B is going to be the 3x1 matrix that consists of the values or the constants on the right. So we have 10 in reference to the first equation, 29 to the second. And at the bottom, we have negative 32 in reference to the last of the equations. And so looking at what we have, again, so I had to determine the inverse of matrix A. And we worked with this just moments ago. And again, the inverse we have consisting of all these fractions here once again. And what we have now, having had already the inverse of A stored, and go ahead and determine the solution matrix X. So I have X is equal to the inverse of A times B. And so just looking at partitioning out, okay, so I'm going to have like 10 over 1/7, negative 11/35, and 19 over 70. 29 is going to be over 1/7, 3/35, and negative 1/35. And I have minus 32 over 1/7, negative 4/35, and negative 9 over 70. And just consolidating, I come out to 1, 3, and 6. And again, this X is the solution matrix. And again, just the general case setup. Okay, we have the 3x1 consisting of X, Y, and Z. And this is going to be mapped with the values of 1, 3, and 6. So X is in reference to 1, Y with 3, and Z with 6. And so we come out to the solution for this 3 equation system, whereupon X is equal to 1, Y is equal to 3, and Z is equal to 6.